Hi, this is your TA Karthike, and today we're going to be studying genetic algorithms, in particular evolutionary algorithms. This is the basic pseudocode for an evolutionary algorithm. So basically, you start with a random population of chromosomes or genotypes which are physically mapped to some physical state in the real world known as a phenotype. Now you evaluate these chromosomes or genotypes based on some fitness or objective function, and then you select parents using two parents using the rank selection algorithm, and then you recombine mutate these parents to produce two offsprings. Then you evaluate your new offsprings, and finally you select individuals from the next generation, and the next generation could contain new individuals. Also, it could contain individuals from the previous generation as well. Now, how does this play out in the context of Pac-Man? So let's just jump into it. So your assignment explicitly says you initialize your chromosome is an action sequence of length 5, and your population is of size 8, which means basically your population is a list of chromosomes, is a list of 8 chromosomes. So you can use this pseudocode to initialize the first generation. Here is the part for initializing a chromosome, and here is the part for initializing the first generation. Note, we keep manipulating this initial generation itself instead of storing all future generation to save space and for the algorithm to be more efficient. I'll be elaborating on this point later on. Now it says to use rank selection to sell. First, it says to sort all chromosomes based on fitness. Now, how do you find the fitness value of a chromosome? Well, it's pretty much the same what you did in Hill Climber. You evaluate each action sequence, and whatever the game evaluation function gives you for that action sequence, that is the fitness value for that chromosome. So, for example, suppose I had a chromosome C1, and this is what it looked like. And you have an initial state, and you have this generate Pac-Man successor. I'll call it GPS just to make it shorter. So I'll get state 1, which is state dot GPS for this action, and then I'll have state 2, which is state 1 dot GPS for this action, and so forth until we reach the end of this action sequence, hence getting state 5. Now, once we reach state 5, we can calculate the fitness evaluation function for chromosome 1, which is just the game evaluation, state to state 5. Now, our current generation looks like this. There are 8 chromosomes in total, and we have each of them has a fitness value. Now we assign ranks to them. So, assuming that chromosome 4 with the fitness value F4 is the highest, then it has a rank of 8. And suppose chromosome 2 with a fitness value F2 is the lowest fitness, then it has a rank of 1. That's how you base the ranking. Basically, the chromosome with the highest fitness value gets a rank of 8, the one below that gets a rank of 7, and so forth. Now, now the main part is how do you select parents? It says you use rank selection, and it gives you an example out here. So basically, what rank selection is trying to tell you is that while selecting parents, you need to select them based on probabilities. So a chromosome with a higher fitness value should have a higher odds of getting should have a higher probability of getting selected. Nonetheless, chromosomes with lower fitness values or with significantly lower fitness values should have some probability of getting selected. So how do you incorporate probability in your code? Well, there are multitude, this could be done in multitude of ways, but I'll be explaining this in a more brute forced approach, and so that everyone can understand it. All right. So suppose I have an array X, and suppose it has 8 eights, 7 sevens, 6 sixes, 5 fives, 4 4 fours, 3 threes, 2 twos, and a single one. So all total it has 36 elements. Now the odd thing you can notice is the probability of selecting 8 is 8 by 36. The probability of selecting 7 is 7 by 36. The probability of selecting 6 is 6 by 36, and so forth. So basically, I've created the array in such a way that if you were to generate a random number from 1 to 36, or since your array indices are from 0 to 35, then the odds of getting 8 are more than 7, and so forth. And the odds of getting 7 are, the probability of getting 7 is greater than 6. So now, so how do you select parents? So you generate a random number between 0 and 35, and whatever num you get, so parent 1, rank of parent 1 will be x of num, and the rank of parent, again you generate another number, random number from 0 to 35, and the rank of parent 2 will be again x of num. But note, like, observe here, calling num again for parent 2, calling random again for parent 2 could again give you 7. So this is wrong because a parent cannot reproduce with itself. So basically, once you have parent 1's rank, you keep generating random numbers between 0 to 35 unless and until you get a different random number. Alright, so suppose I get parent 1 rank 7 and parent 2 rank 8. But suppose if I had 7 again, then I would have again generate a random number unless I get a different one. So now suppose we have two ranks for our parents. Parents 1 rank is 7. Parents 2 rank is 8. So this implies that chromosome 7 and chromosome 8 will be chosen to produce offsprings, and you can say your offspring generation will be again a new list of chromosomes, and from here on I'll be abbreviating the offspring generation as OG just to make it shorter. Now comes the crossover process. So remember that two parent chromosomes produce two os- two offspring. So basically, to have 8 children, you need to repeat this process a total of 4 times. Basically, getting two parents, producing two offsprings, and do this 4 times until you have an offspring generation of 8 chromosomes in total. So suppose I selected CX as my parent 1 and CY as my parent 2. You can call them C7 and C8 as well. C7, C8, doesn't really matter. And your new child chromosomes are these empty list. My bad for the spelling mistake. Now your assignment explicitly says that you do a random test, and if it is greater than 70%, you don't technically generate new offsprings, you just keep the original parents in the new population. So if I generate a random integer from 1 to 10, and if it's greater than 7, so what I do is all I say is that my child is my child 1 will be my parent, and my child 2 will also be the parent, and I just append these into my offspring generation. Because if it's greater than 70%, you just keep the parents, you don't generate or reproduce more. Now if it is less than 70%, then yes, then you need to do a crossover. And for a crossover, it clearly says that you need to do another test, and if the test is below 50%, the gene will be donated by X, otherwise by Y. So if it is less than, suppose if the test is less than 70%, so we come here and we just randomly flip a coin while iterating through one of these childs. And if the result is a zero, that is, if it's a tail, you could say, then child's one child one's gene will be from parent X as shown, and child 2 genes will be from parent Y. And if it's a heads or a 1, then child 1's gene will be from parent Y, and child 2 gene will be from parent X. All right, so this is the code for crossover, and you need to do this a total of 4 times so that you have a new population of 8 individuals. All right, now once you have filled the OG with 8 individuals, then you apply mutation. Now how do you do the mutation? Suppose you have this OG which is C prime 1, C prime 2, C prime 3, dot dot dot, C prime 8. So all you do is you iterate through your offspring generation. Again, you do a random test. Now, if this test is greater than 10%, then there's no mutation to do. You just leave it be. But if the test result is less than equal to 10%, that is if k is equal to 1 out here, all we do is we generate another random integer k prime, which is equal to from between 0 to 5. And suppose your chromosome to be mutated is OG of I. So all we do is chromosome to be mutated k prime possible, and you just select some random integer from the list of possible actions, and you just basically, if the test result is 10% or less, all you do is you take your chromosome and you mutate one of the actions in that chromosome, just one action. And that's what this part is doing, this pseudocode here. Now that we are done with the crossover and mutation, this is the part where I was basically telling you that we are trying to save space. We aren't like storing all the future generations, so we initialize this generation above, right? So now all we do is we have a new offspring generation, and we just replace the current generation with the offspring generation. That's it. And you keep doing this until you reach the limit of generation. And obviously, while you run this algorithm, you also need to keep track of the best action sequence so far among all generations. And once the limit is reached, you return the first action of this best action sequence.